In this video, we'll discuss the bending of a cantilever. And if you have heard the cantilever term for the first time, then let me tell you that let us assume that there is a steel rod which is embedded deep in the wall, and some of its part of length L is coming out of the wall. Now, when you must have seen that it behaves like a spring when we vibrate this end with some force, and when we are applying some load on this steel rod, then it bends like an arc, and this end depresses by some distance. So, in this video, we are going to calculate this depression of cantilever. Now, first of all, you can see that let us assume a small distance x from this end, and let us assume a small element which is this one dl, and as it is a curved element, therefore there would be some center of this curvature, and this angle is theta, which is very small. Theta is very small, and hence this angle would also be equal to theta, because we can say that these two angles are equal, because when this cantilever was straight, then this angle and this angle was 0. Now let us assume that this part of this cantilever has been depressed by a distance of y. Now first of all, we write down that this is L minus x, this distance is L minus x, and let us draw this diagram that this is dl. So so this is dl, and this small length is dy, and this small length is dx. So you can imagine that this is dx and this is dy. Okay, this length is dx and this length is dy, not y. Okay, so this angle is also theta. So you can say that dl cos theta is equal to dx. The element of the component of dl along this one is dx, and therefore dl by dx is equal to 1 by cos theta. And for small angles, cos theta is equal to approximately 1. So for small angles, dl by dx is equal to 1. Now we know that dl is also equal to r into theta. This angle, this is radius r of this curvature, and this angle is theta. So we can write that dl is equal to r into theta. Now if we find out dy by dx, then you can say that dy by dx is equal to tan theta from this triangle, and for small angles tan theta is approximately equal to theta. So dy by dx is equal to theta. Now we know that from this equation we can say that theta is equal to dl by r. And if we double differentiate this equation, then d square y by dx square is equal to dl by dx into 1 by r. Now we have already written by equation number 1 that dl by dx is equal to 1, and therefore d square y by dx square is equal to 1 by r. Now let us name this equation as equation number 2. Now we know that the torque of this load about this point will be this perpendicular distance into w. So it would be w into this perpendicular distance, which is L minus x. Okay, this torque has bended this cantilever, and we have already discussed that the bending moment, which is obviously a torque, developed in a beam or a cantilever bending moment. We have already discussed that it is equal to this one. You can see that this is gamma a k square by r, where a k square is ig, where ig is the geometrical moment of inertia. So this is gamma ig by r. Gamma ig by r. This is the bending moment developed due to this bend. So in equilibrium condition, we can say that in equilibrium condition, this bending moment will be balancing out the torque of this weight W, and therefore WL minus X, W into L minus X will be equal to gamma Ig into 1 by R. Okay, now we have already calculated the value of 1 by R, which is d square y by dx square. So 1 by R, which is d square y by dx square, is equal to W upon gamma Ig into L minus X. Okay, this is W into L minus X upon gamma into Ig. Now you can integrate this term, both the sides, that integrating d square y by dx square, and here it is integration of W by gamma Ig into L minus X, okay, into dx. So integrating this would be dy by dx, and it would be W by gamma Ig, and this will be L x minus x square by 2 plus some constant c. Now you can see that at x is equal to 0, this is x, and at x is equal to 0 at this point A, this rod is horizontal and dy by dx is 0. So at point A, x is equal to 0 and dy by dx is equal to 0. So we can say the value of c will be 0. So dy by dx will be equal to W by gamma Ig into Lx minus x square by 2. Now again integrating this expression, we will get y, and y will be equal to W by gamma Ig, obviously with respect to x. Then it would be L into x square by 2 minus x cube by 6 plus another constant. So again at x barabar 0, x equal to 0, y will be 0. You can see that at this point there is no depression in the cantilever. So the value of this c is also 0. So y will be equal to W by gamma Ig into L x square by 2 minus x cube by 6. Now we have to calculate the depression in this part, which is, let's suppose it is del. So at this point B, we can say that B has depressed down by a distance of del, and at B x is equal to L. So at B x is equal to L and y is equal to delta. So depression at this point will be del equal to W by gamma Ig, and you can see that if you substitute the value L here, then it would be L cube by 2 minus L cube by 6. So it will be equal to L cube by 3. So this is the depression produced in a cantilever by a weight W, and this gamma is the Young's modulus of the cantilever, and Ig is the geometrical moment of inertia, and L is its length. Now in the next video, we'll use this conclusion to explain that why I-shaped beams are preferred. Thank you.